Hey, Physics 30s, Mr. Jukley here, going through Unit 4, Lesson 4, which is all about refraction. And you may remember from Physics 20, we very briefly talked about refraction, and that's the bending of a wave as it goes from one medium into another medium. So, things you can try out at home, well, I guess you can't really go to the pool right now, but things that you can try out at home is if you have a glass of water, and a pencil or a reusable straw or your finger even realistically, and you put it at an angle, you can actually see this is a classic magic trick, the broken pencil trick. So it's going up here and then it looks like it's broken, it's moved over. That's because of the properties of refraction. Same person where this on the right hand side over here, essentially it looks like this person has lost their head. Oh, you can't really see that very well. Looks like this person has lost their head. The person's camera, so the lens for the camera, is half in and half out of the water. And we see that refraction based on in the water versus out of the water. There's also some magnifying properties going on here, which we'll talk about a little bit later when we talk about lenses. But yeah, you can try this one out, and later on in the lesson, we will do our best to describe it. So, there we go, back to normal. What we want to do is consider a ray of light going from one medium to another at an angle. So from medium 1 to medium 2 at an angle, when the medium changes, and here's the big question, back to lesson 1 even, when the medium changes, what property also changes? And I'll give you a little bit of hint here. We've got our universal wave equation, V is equal to, so that speed is equal to frequency times wavelength. So hopefully you're remembering that the frequency never ever changes. That one stays the same once the wave leaves its source. If you're saying it's the speed that changes, and I mean also the wavelength would correspond to that as well, but the speed changes when it goes from one medium to another. So when we look at this, if I go from a fast to a slow medium, it's, there we go, a fast to a slow medium, its speed is changing, and that's what's causing it to bend. And in this particular case, we're going from a fast medium to a slow medium. If I were to draw a normal line on this, I don't know why I don't have a dotted line that's just not got any arrowheads in it, but if I were to draw a normal line, we'd also notice that it's bending closer to the normal line. So my incident angle, which I'll draw in blue, theta I, is definitely bigger than my refracted angle. And remember, we're going to use capital R for refracted. Lowercase r was for reflected wave. And it's definitely bent closer to that normal line. Again, the normal line, 90 degrees to the surface. Cool. So if we wanted to look at a good example, a good way that you can kind of remember this, I just need a bit of extra space here. If you ever watch Trailer Park Boys, it's kind of a highly inappropriate show for school, but there's the guy Bubbles who's always stealing shopping carts and then returning them. So if we've got shopping carts and you're trying to steal a shopping cart, and we've got the grass over here and we've got the smooth concrete over here. Here's a way that you can kind of remember this and a good way to think about this. So we've got grass, which is a slow medium, and smooth concrete, which is a faster medium, and then you've got your shopping cart and you're trying to push your shopping cart at an angle from the concrete onto the grass. And then you've got your four wheels in the shopping cart. This is probably the worst shopping cart drawing you've ever seen, but that's okay. You can still picture what I'm trying to do here. So you're trying to push it at an angle like this, and initially your speed is looking like it should be going this way. But the very, very first wheel to hit, I'm going to color that one in blue, the very first wheel to hit is going to slow down before any of the other wheels slow down. So what that's going to do is if these wheels on this side that I'll color in green are going faster than this blue wheel, it's going to cause the entire cart to shift and to turn closer in this direction, so closer towards our normal line. The exact same thing happens with light, because well, we think about it in terms of just this single ray. Realistically, it's not one single ray, it's a wave, and there's part of that wave that's going to hit first. So this part of the wave is going to get hit first. It's going to slow down. This part with the big bulb on the end, I guess, is going to slow down, which is going to cause this part to go faster. And if one side's going faster than the other, it's going to bend in this case, towards the normal line. So I hope that makes sense for people. Now, when we're talking about the speed of light through a medium, we often talk about the index of refraction, or the optical density. So index of refraction, optical density are often used, those two terms are often used interchangeably. The index of refraction is essentially how easy light has passing through a particular material. So our formula for this is fairly straightforward. N, our index of refraction, or our optical density, is equal to c divided by c. C is the speed of light in a vacuum, or we often assume that air is close enough. And for most purposes, it's pretty close to the speed of light in a vacuum. And we know that that's 3 times 10 to the power 8 meters per second, 300 million meters per second. And then V is the speed of light in the medium. So that's the other medium. That could be water, that could be glass, that could be diamond, that could be all kinds of different things. But that's the speed of light in the other medium. So just kind of thinking about this, air has very, very little resistance, right? So it's very close to our optical density of a vacuum. Very, very, very little resistance. So when you think about this in this formula, essentially we've got is our optical density of air, well, that's C divided by V, right? So C, the speed of light in a vacuum, V, the speed of light through air. But if they're the same speed for all intents and purposes, or for at least our course, they're going to look like they're the same speed. Well, that's realistically C divided by C, and C divided by C, whatever number that is, in this case 300 million meters per second, is just going to be equal to 1. Cool. So the optical density of air is equal to 1. That is something that you should know. That is something that you should memorize, because it won't be given to you in questions and things like that. So know the optical density of air. Just take a minute to think about this. Are all the other values going to be bigger or smaller than 1.00? Or in other words, is 1 the biggest value or the smallest value? So let's think about this. If C is the fastest they can go through a vacuum, and we're saying that air is pretty much the same thing, they got to be going slower through water, slower through glass, slower through diamond, slower through plastic, slower through all those different things. So if we have a smaller number in their denominator up here, that means we're going to have bigger values. So this should be the smallest N value that we see, smallest optical density that we see. So just kind of keep that in mind, which is kind of what we're talking about here. Pretty much everything else moves a little bit more slowly. Water's more optically dense, diamond, all those different things we mentioned is more optically dense. So let's check out a quick example here. We get a laser that is shone through water, and it's telling us that the water has an optical density of 1.33. It reflects off a distant object and returns in a total time of 183 microseconds. Determine the distance to the object. Well, this is light, and light travels with uniform motion, so we're clearly using v is equal to d over t. But the speed, we don't have the speed yet, do we? So I think what we want to do is we want to use that brand new formula and say n is equal to c over v, and try and figure out what the speed through water is. So let's just rearrange that. V must be equal to c over n. We know that it should be smaller, so hopefully when we divide this out, it should be smaller than 300 million meters per second. So 3 times 10 to the power of 8 meters per second divided by 1.33 as our optical density or index of refraction. So that works out to be, when we plug it in, 2.2556 times 10 to the power of 8 meters per second, which is slower, which is perfect, exactly what we were expecting. Let's see. Then it reflects off a distant object and returns in a total time of 183 microseconds. So let's just sketch that one out. So it's starting here, start, reflects off of a distant object, so it goes all the way there. That's our one-way distance, and then it comes all the way back in a total time of 183 microseconds. So if we wanted to really think this one through, we're just looking for how far away it is. We could either do 2 times the one-way distance, so we could say v is equal to 2 times the one-way distance, divided by the time. Cool. Or we could just cut that time in half and say, well, if it takes 183 microseconds to go all the way there and all the way back, it would take half as much time just to go all the way there, and then we'd end up with that one-way distance as well. So honestly, it doesn't matter how you solve that as long as you're taking into account that it's going all the way there and all the way back in some way, shape, or form. So I'm going to say, well, the time one way is equal to 183 microseconds divided by 2. So I'm going to plug that into my calculator, and I think I get 91 point, whoops, 91, start over again there, 91.5 microseconds. Cool. Now I can say V is equal to D over T, and again, that is the one-way distance with my one-way time. So the distance must be equal to V times T. Okay, no problem. So V we just figured out 2.55, wow, lots of screw ups in this one. 2.2556 times 10 to the power of 8 meters per second times, okay, microseconds. That's a little weird. I don't really want microseconds. What I really want is 91.5 times 10 to the negative 6 seconds, because micro is 10 to the negative 6. And then finally we plug this in. You'd expect it's light. You'd expect it's going very fast, regardless if it's a little bit less fast than through air, but you'd expect a pretty big distance. So 2.06 times 10 to the power of 10 meters. So in 91.5 microseconds, it goes a ridiculously long distance, which is, well, it's expected. Oh, but hold on. I made a bit of another screw up. Lots of screw ups in this one, but that's okay because I've got an eraser and they are easy to fix. It's not 2.06 times 10 to the power of 10. I forgot to add the micro in there. It is 2.06 times 10 to the power of 1, 2, 3, 4 meters, which is a little bit more reasonable, but still a very, very long distance, or 20.6 kilometers, which matches with a lot more of the calculations that we've done in previous lessons. Perfect. Glad I caught that one before I moved on. So anyways, there you have it. Just a little bit of new stuff with the new formula and the idea of optical density. Cool. So next thing that I want to look at here, and this is just PhET. If you search PhET, you can look for all kinds of really cool animations for this. They do fantastic work. So some of the things that I want to show you with this is just what happens when we're going from one medium to another medium. So I've got a laser pointer, and my laser pointer I can move around, and I can say, oh, hey, look at that. There's a laser pointer. Very, very cool. And we see, so the top material that we see up here is air. So I don't know if you can really see my finger or not for this one. You can't. But the top material is air, the bottom material is water. And then we can see as that laser travels through the air and goes into the water, it bends towards the normal line. Notice with this that if there's no angle of incidence, so the angle of incidence is 0, the angle of refraction is 0. The larger the angle of incidence, the more the light actually bends, right? Obviously, the refracted angle is going to get bigger as well, but the more it bends. So we go from no bending a little bit to more bending. So the larger the incident angle, the more bending we typically see. Perfect. Okay, let's check out what would happen if I switch the bottom. So right now it is currently air on the top, water on the bottom. Let's change it to something with a higher refractive index or a higher optical density. I'm going to change it to glass, and then look what happens as I went from water back to water and then to glass. You'll notice that the bigger the difference between the two optical densities, the more bending there actually is. And I can slide the scale on the side over here. So air to air, well, it's the same optical density you would expect, no bending. But as I increase, Notice I'm increasing my optical density of the second material, and the bending becomes more and more and more and more. So the larger the difference, the more bending we actually see. Perfect. So again, we're going from, in this case, a fast medium to a slow medium, and we see it bending towards the normal line. Any idea what would happen if I went from a slow medium to a fast medium? So slow on top, so let's set that one to water. Oh, that's glass. Let's set one to water. And obviously water to water, no refraction whatsoever, same refractive index. But let's set the bottom one to air. And we'll notice now that we're bending away from the normal line. And that's something that's very, very important for us, is to understand if we're going from a fast medium to a slow medium, it's bending towards the normal line, or a slow medium to a fast medium, it's bending away from the normal line. And then same sort of thing that we looked at before, the larger the incident angle, so very small, actually zero incident angle, the larger the incident angle, the more bending we actually see of that light wave. Perfect. And also same thing, I guess I could show you this as well. The bigger the difference, just put it there, the bigger the difference between the two, so let's set that up there, the more bending we actually see. So from same optical density up to the maximum difference that we can actually have, bigger the difference, the more bending of light we see. Perfect. So we've seen some patterns there. Feel free to log into PhET. This one's just called Bending Light Animation. It's pretty cool to play around with. If you were in the classroom right now, I would definitely show you using some laser pointers and some other things. But this is a pretty good substitute. So in summary, if we're going from fast to slow, we always go, what is it, away from or towards the normal line? So I'm just going to draw a normal line straight through there. If you're saying it's going to bend towards the normal line, that's perfect. So without any bending, this is where it would pass, but it has bent, not bended, towards the normal line. And again, why? We already kind of talked about this. This part over here slows down first. So this part's going faster, blue part's going faster, black part's going slower. It's going to bend around in that direction. Cool. From more dense to less dense, you probably actually noticed with this a little bit of a reflected ray in this one as well. So from more dense, from slow to less dense, which is fast, we are bending away from the normal line. And make sure, this is where it gets really important, capital R for refracted ray, and then lowercase r from reflected ray. Cool. So lots of review there. So you've got this one in your workbook. Can you predict the direction of the refracted ray out of the glass rectangle? So if you want to take a minute and put it on pause and try and figure it out, maybe use an eraser just in case, but you can absolutely do that. Put it on pause now. Otherwise, let's go through and let's check it out. So this is coming up, and it's going to, not the prettiest one I've ever done there, but there we go. So it's going to hit the glass there. Let's get another one here. I'm going to draw a normal line. So I'm just going to draw this in blue, and it's going to be freehand, so it might not be perfect. So there's my normal line. And I know if it's going from air into glass, it's going from low optical density to high, or it's going from low to high, or it's going from fast to slow. So I know that it's going to bend towards the normal line. So it would have originally gone at an angle like this, just following straight along if it was the same optical density, but I need it to be bent towards the normal line. I'm going to do that pretty extreme right there and just be very, very clear that it's towards the normal line. Then as it exits the glass, now we're going from a high optical density or slow to a lower, oops, that is not at all what I wanted. Just get rid of that arrow, I suppose. Go away, arrow. It is going from a high to a low optical density, or from a slow to a fast, and we know that it is going to bend, in this case, away from the normal line. So I'm just going to draw another freehand normal line, try and make it as perpendicular to the surface as possible. get my arrow drawer out, and if it's bending away from the normal line, it's going to bend away something like this. Now the amount that it bends, I did something very specific there. The amount that it bends away from the normal line should match so that my incident angle going in matches my refracted angle going out. So this red angle right here should match that one there because it's bending the same amount going in as it is going out. Cool. So there we have it. If I go back to this bending light animation, we can actually see this here, right? So I've got a square prism, and I've got my my laser pointer. I can move and rotate this laser pointer however I want. So 0 angle of incidence means 0 refraction, just passes straight through. But then if I start to put this at a bit of an angle, we start to see how it bends and how it moves through. And you'll notice that the incident ray, the original incident ray, is parallel to the overall ray that comes out. Cool. Okay, so there's that one. Let's have a look at, I believe it's this. Let's have a look at the next one. This one's a little bit trickier here. Predict the direction of the refracted ray out of the glass prism. So same sort of thing I want to look at here. I might use a dotted line, even though I don't have a dotted line. It's not an arrow for some reason. Can I do that? Oh, maybe. Maybe. Might have figured it out. Nope, not at all. Not at all. Okay, grab that. Grab that. Get that. No, it's still nothing. Okay, that's fine. Whatever. I'll just do it in a different color. So my normal line, there we go, has to be 90 degrees to the surface. So let's just make that 90 degrees and move it up to an appropriate spot. There we go. So 90 degrees to the surface. Now, if it's going from a fast medium to a slow medium, and again, you can put this on pause if you want to try this out on your own. But it's going from a fast medium to a slow medium. So it's going to bend towards the normal line. So it would have originally, if there was no change in optical density, it would have gone straight like this. But it's going to go towards the normal line, so from fast to slow towards the normal line, and it might be going down at an angle something like this. So again, blue was my normal line. Cool. So next thing I want to do is if I want to figure out how it's actually leaving, let's go grab another blue line. I need another normal line, and it needs to be 90 degrees to the surface. So that's about there. And then I'll just move it into position there. So normal line, always 90 degrees to the surface. Now, if it's going from, let's see, from now slow to fast, we know it's going to be bending away from that normal line. And if it's bending away from that normal line, let's go back to the line drawer here, bending away from the normal line. Here's where it would have gone if there was no change in optical density. But if it's bending away, it's going to be bent downwards away from it. So we might see it coming out something like that. Cool, so I hope that makes sense. Actually, you know what, let's check it out one more place. This thing, this is pretty cool. I really thoroughly enjoy this. So let's get a triangular prism. Let's first set this thing up so that it's going completely horizontal, perfect. And let's put that triangular prism in its way, and that is, there we go. That is pretty much what we see happening there. So from fast to slow, it bends towards the normal line, and then as it leaves, it's going from slow to fast, it bends away from the normal line. Cool, very cool. Last couple things to go through with this. Just a couple of those applications. So the broken pencil, and actually I think there's a bit of an animation for this one. So let's just be patient with me here. There we go. And start this thing up. There we go. So essentially what happens here with this, is the animation working? There we go, just very slowly. Very slowly. Gives you lots of time to read it. There we go. So bends away from the normal line, from the eye. Excellent. And then it says the pencil is going to be over there, but only in the portion that's in the water. Very cool. That was brutally slow. I might get out of this and and not worry about that so much anymore. Go back to the thing that I can actually write on. Sorry, buddy. That's a bit of a miserable system that I've got going here for that. Not the smoothest video I bet you've ever seen. So anyways, if you got your eye over here, right, realistically, you've got this light coming out from the pencil. So it comes out here, hits a normal line, the normal line perpendicular to the surface here, and bends away from the normal line. Now your eye, thinking that light travels in straight lines, is thinking that the pencil is actually over here. So should have just drawn it in the first place, to be honest, but hopefully that makes sense for people. Okay, very last activity is, you know when you're at the pool and you think that you can swim down and grab the little rings that are, that, you know, they sink and your job is to dive down and get them, but the rings always look like they're not as deep as they actually are. Could we explain why they're not as deep as they actually are? So like this treasure chest that this guy's spotting from his boat, he's like, oh yeah, treasure, perfect. I'm going to swim down and grab that. It doesn't look as deep as it actually is. Could we explain why? So the treasure chest is obviously on the bottom of the ocean or the bottom of the lake or whatever it is. So it's down here. And the treasure chest is giving off these light rays. And I'm just going to trace one of them that's going like this. And then it's going, so that light ray is now going from a optically more dense to an optically less dense material. Or in other words, from a slow to a fast material. And we know that it's going to bend away from the normal line. So if I just draw a normal line right here, it's going to bend away from that normal line. And if it bends away from the normal line, it's going to look like this. Now, this one arrow, the gray arrow that I'm kind of focusing on, because it's the one pointing at his head as opposed to pointing at his stomach or crotch or whatever the other one is, if he's thinking about, where is that stuff? His eyes are going to perceive it coming from, and I'll highlight it in black, coming from over here, which is not nearly as deep as the treasure chest actually is. That's when you guys swimming, things don't look as deep as they actually are when you're looking at them from an angle, which is pretty cool. So that is it for this lesson. Apologies, it was a little bit of a scramble there in different places, but do your practice, check it out, and let me know if there's any issues. So that's it for now. We'll talk to you again soon, Physics 30s.